Hello, my name is Vaibhav Fadnis. Welcome to this session on how to build smart robots and operate them easily using AWS robotics services. Robotics and autonomous systems are key elements of digital transformation in many industries. All trends point to strong growth in autonomous mobility in just the next few years. There are specific industries where we see robotics playing an important role. These include logistics, construction, retail, hospitality, healthcare, agriculture, oil and gas, consumer home products, to name just a few. Let's also take a quick look at some of the key trends in the industry that we've been observing as we work with several customers over just the last 2 years. First, a notable trend is that a number of robot startups are accelerating development by embracing open source hardware and reusable components with software platforms such as Robot Operating System or ROS. Second, a number of robot manufacturers use AI, artificial intelligence, and machine learning to teach the robot new tricks, so to say, to make them smarter. Third, connecting robots to the cloud helps them leverage cloud services for better customer experiences. A fourth trend we have seen is robotics as a service has been emerging as a new consumption mechanism as new business models emerge. And finally, cloud is certainly a strong enabler. The cloud helps make robots smarter, operate them easily. Cloud can help in a variety of use cases. However, the difficulty of setting up a secure communication layer between the robot and the cloud prevents customers from really leveraging the benefits. Customers are also looking for guidance on how to make the best use of several different services for addressing specific use cases. So, in this session, we will look at reference architectures and a few customer examples. Of the top cloud robotics use cases, first is data ingestion, storage, and analytics. Robots do generate and collect a lot of data, and analysis of that data is important in surveillance use cases. But how do you build an architecture that can ingest multiple data sources into a single data store? Second, streaming video from the robot can be effective for teleoperation, but how do you build a low latency video connection from the robot to the cloud? Third, robots can be smarter if they leverage pre-trained ML models with inference at the edge, but then you need an easy way to deploy these models from the cloud to the robot. Fourth, the cloud can help keep the robot software up to date, but it needs a reliable and a secure connection to the cloud. Now extend that to multiple robots, and it's apparent that the cloud can help monitor fleets of robots. And finally, the cloud can also help test robot applications in the cloud in simulated environments. So let's look at these use cases briefly along with reference architectures. Each of the cloud robotics use cases we talked of, first off, requires some foundational elements, and AWS IoT services are really that foundation. One of the foundational elements is secure connectivity to the cloud, and AWS IoT Greengrass is a flexible edge runtime service that helps you connect robots running at the edge to the cloud. With a simple provisioning command, Greengrass creates and manages the permissions that are required for that secure connectivity to use cloud resources. Then you can use built-in features for data and state synchronization, stream management, ML inference, over-the-air updates, and so on. Greengrass does this by extending AWS services to the device, and it really helps you keep the data where it needs to be. You don't need to transfer all the data to the cloud. That both helps with laws of physics, keep data where it is generated, and laws of economics, save the cost of transferring data that you don't have to send. Storing data locally and executing applications locally also can help with adhering to regulatory and sovereignty requirements. Some of the architectural components of IoT Greengrass, the latest version 2.0, are components, recipes, and deployment artifacts. Components are flexible, runtime agnostic software modules. A component can represent an application, a runtime installer, a library, or any code that you would run on the device. Recipes are component metadata that include instructions to install, run, and shut down components. And deployment artifacts are the actual software code, the software bundle, the container image that you may be running. With that foundation, let's now take a quick look at the use cases. Let's start with data ingestion. The challenge that most customers have highlighted with data ingestion is the variety of sensor data that robots collect across still images, video, as well as location and motion data from the IMU. There's multiplicity of data sources, multiplicity of data types, and then customers want to run real-time analytics as well as analyze some of the data in a batch mode for later analysis of surveillance type applications. The solution that we offer includes pre-validated workflows for ingestion, processing, and even analytics. We offer fully managed dashboards and analytics services. And we have specific solution architectures for individual use cases. As an example, here's an architecture pattern that's common to ingesting large amounts of data. The core tenet is having a central landing zone for that data. Once you have different types of data collected in that landing zone, you can then separately process data in either the batch mode or in real-time mode. For example, you may want to track robot performance over time across a variety of use cases and tests, and you could use this information to understand if the software updates are improving customer experience. You could use this for surveillance and inspection workflows, so you really want to understand if there was an anomalous behavior and want to analyze that in spatiotemporal sense later. On the other hand, in the speed layer, you could capture and process data, making it immediately available for an operator to view in a dashboard, so the operator could know where the robots are and how well they're functioning. So our architectures can enable a landing zone to ingest the data and then enable both batch and real-time or near real-time processing. As an example of an architecture, I mentioned Greengrass with components. So in this case, we use a public component for reliably capturing and ingesting data. The Stream Manager public component has multiple AWS integrations. And in this case, in this architecture, we're going to look at Kinesis. Stream Manager is integrated with Kinesis that then allows you to have a flexible and massively scalable data landing zone in the cloud. In the batch layer, you could store data in Amazon Storage Service S3 or purpose-built analytical databases. These tools are also integrated with Amazon QuickSight and Amazon SageMaker for dashboarding and model training, respectively. In the speed layer, you could process and then store data in a variety of high-performance databases, such as Amazon's DynamoDB or Amazon TimeStream. But then these are just a couple of options. There's a number of other AWS services that could be used for data ingestion solutions. Let's take a quick look at video streaming use cases, typically useful for teleoperation and supervision. The challenges here are firstly requiring a secure data link for sending commands to the robot, and equally importantly, a low latency link for video streaming. Now you could use multiple discrete tools, but it's hard to stitch together an end-to-end solution. The AWS Robotics suite of solutions helps with establishment of a low latency peer-to-peer communication using Amazon Kinesis video streaming with WebRTC that provides you an end-to-end solution. It also has multiple channels, so you could use a video channel for the video data and a data channel for the teleoperation data to the robot. Here's a quick example of an architecture for this solution, and there's really three aspects to consider: the interface for the end user, the robot itself, and the cloud. In this architecture, we deploy the solution to set up WebRTC as a component using Greengrass, and then setting up a signaling channel per camera, which will allow AWS to create a peer-to-peer connection with the robot from the cloud. So the user initiates a connection request to the robot from the application. AWS then establishes the signaling connection to the endpoint that allows secure connectivity. And once that connection is established, we now have a low latency video channel available to see what is really happening with the robot. So now you're able to teleoperate the robot and actually view the robot in operation. Let's look at a third use case, this time for machine learning inference at the edge. Robot manufacturers and robot users both want to train their robot to identify objects in its environment and make that inference at the edge based on a pre-trained ML model. Now, this would require access to tools for large-scale machine learning in the cloud, as well as a way to securely deploy these models to the robot for inference at the edge. The solution we offer includes Amazon SageMaker, which would train the ML models in the cloud for obstacle detection and other such use cases, as well as SageMaker Edge Manager with Greengrass, which would provide a reliable and secure way to deploy those models onto the robot. So in this conceptual view, a variety of data from the robots is collected into a single repository, which can then allow pre-processing and labeling at the back end. This data feed then allows the ML model to be trained using AWS SageMaker and other AI ML services, and the updated models are then uploaded into the catalog for further deployment onto the robot for inference at the edge. A common use case is the Boston Dynamics Spot robot, and this robot is very commonly used for autonomous inspections to discover anomalies, discover leaks, and compliance checks, and so on. They're often running in difficult, dangerous situations. So we worked with Boston Dynamics to create and run a cloud-trained ML-enabled application using Greengrass. So first off, we built an ML model to detect objects such as bicycles, cars, fire extinguishers. We captured raw video training data to train the model. Once the models were ready, we used IoT Greengrass to deploy them to the Spot robot. And once these components were deployed, you would see that a number of Greengrass components are running in a container and interacting with the Spot SDK. So we have not only used AWS services, but also integrated them with the Spot SDK. That was a quick look at machine learning use cases. Let's take a look at software updates to the robots. Every robot manufacturer we have talked to, without exception, has a need to be able to deploy updates to the robots remotely over the air and do so securely. But the challenge there is having a reliable and secure channel communication layer between the robot and the cloud. As you've already heard, IoT Greengrass does that. It offers a secure, reliable, modular, component-based edge software management model. So with IoT Greengrass, you can also do credential management, and IoT Greengrass offers several public components that are available for common robot software requirements. So let's take a look at that. IoT Greengrass has been, in the most current version, been enhanced with enterprise-grade features such as configurable deployment rates and failure thresholds. So you could set thresholds that must be met for deployments to go through. You can start with a small subset of your entire fleet, make sure that the failure thresholds are being met, that is successful, and then scale out to the rest of the fleet. On the edge, Greengrass can detect if the component has been deployed and executed correctly, and can also do additional custom verification logic, such as checking if the web server component was installed correctly. Greengrass also exposes event hooks to perform additional validation before deploying a component. So it could check if the robot has sufficient battery level before it initiates a deployment onto that robot. So a number of these functionalities together make the deployment capabilities enterprise ready. With Greengrass, all of the deployment actions are also available through an API. So as this architecture shows, you can connect that API and integrate Greengrass deployments with your CI/CD pipeline. Once the software artifacts are built and tested, ideally decomposed in a set of modular components, they can then be deployed to fleets of robots. And the software agent running on the robot would receive the update and then manage the local application lifecycle, such as start, shutdown, and recover. Greengrass can also run components offline for periods of time. A quick look at the number of public components that are available. These are pre-built AWS provided components that provide you common functionality you would need. It spans edge capabilities for running ML models all the way to securely connecting to your robot so you don't have to SSH into them. Seafloor Systems is one of our customers who wanted an over-the-air update solution. They worked with us to build a solution using RoboMaker, AWS RoboMaker, and AWS IoT Greengrass to build and manage their USVs, or uncrewed survey vehicles. With this solution, they could save hours of effort per robot, and they could deploy their application to the robot in minutes. More details of this case study are available on our website. As another quick example, AgroIntelli, which is a startup based in Denmark, they make cloud-connected agriculture robots for precision farming. Naturally, the robots run in remote locations such as farms, making it difficult to update them. We worked with AgroIntelli using IoT Greengrass 2.0 to deploy and manage their software in a reliable and secure connection, in a secure way. Now, they have deployed their entire fleet using AWS IoT Greengrass. Let's take a quick look at fleet monitoring. Having deployed software over the air, you now want to be managing a fleet of robots. Robotic engineers and operators look to collect insights into the fleet operations and collect health metrics to take actions before problems occur. By connecting robots to the cloud, engineers and operators can remotely monitor and supervise without requiring to be there. But the challenge is to have that secure connection and have the right dashboarding capability, which reflects the real-time status of the robots. With the AWS solution, developers can use device shadows, which is JSON-based state object that are securely synchronized between the state of the robot on the physical device and the state of the robot as shown in the cloud. Robots that are provisioned with AWS IoT Greengrass have device shadows ready to use out of the box, enabling you to connect your current end-user facing application with existing fleet monitoring and dashboarding tools for robots in the field. In this architecture, you would see that fleet monitoring solutions can take away the heavy lifting by leveraging device shadows. We have 3 robots, each with a device shadow that reports the current battery level by synchronizing the local device shadow with that stored in the cloud. Once it's set, desktop, web, or mobile applications can access the device shadow in the cloud at any time without having to connect to the physical robot. And you can then set rules on device shadow updates to automatically alert your team over SMS or email notifications when a threshold is met. So you will notice robot named ROB02 has a low battery level of 10%, and that could trigger a notification. Let's take a look at one final use case, which is simulations. The development cycle for robot applications usually starts with developing the application on the robot and then test and simulate that application in a simulation environment. Simulations enables all developers to easily access a virtual robot for testing the application and algorithms without requiring access to expensive physical robot equipment. The AWS RoboMaker service enables developers to run simulations in the cloud with a simple API call, and that can be integrated with automated test workflows. Now, developers will typically iterate many times in simulations to get the application working as it should before deploying the code to the physical robots. Then once the code is ready, the development teams can use Greengrass to automatically deploy the release code to test fleets of real robots for further testing and validation on the ground. So here's a quick example of a simulation running in AWS RoboMaker. You see multiple robots going around in a warehouse simulated world. Now, developers would have access to a common development environment, common development tools that are connected to the application which is running in the cloud. These tools could include a Gazebo simulation engine. It would include RViz and RQT-like visualization tools, or even a terminal to interact with the application. Through all of this through the AWS console. With recent functionality added to RoboMaker, customers can also bundle in and bring in their own tools. Naturally, a core benefit of running simulations in the cloud is by using API calls to programmatically run hundreds of simulations in parallel. So when using simulations for automated testing with a CI/CD pipeline, developers often want to build in parameter sweeping and run simulation tests in batches. Developers would want to cover as many conditions as possible, catch bugs before they create issues in production. Thus, using these environment variables and the batch simulation API of AWS RoboMaker, customers can now automate running these simulations in parallel for a number of scenarios and run tests with different parameters. All of this with simple API calls. You can now integrate that with your CI/CD pipeline so that successful tests are automatically moved forward into the CI pipeline and can be used to deploy to robots in production. Here's an example of a customer, iRobot in this case. With over 5 million units actively deployed, iRobot uses AWS RoboMaker in their continuous integration pipeline to easily scale and run hundreds of tests in simulations for each software release candidate. They are able to reduce costly and time-consuming physical testing and provide test scenarios at the developer's fingertips. This video shows a simulation of an iRobot Roomba robot running in a virtual AWS home world. It's a virtual world. It uses synthetic sensor data to navigate around obstacles. So now you will see it's able to detect a couch, detect walls, and navigate around those for cleaning. The ability to test applications in this kind of a simulated environment greatly accelerates test cycles and saves money. All right, so that was a quick little teaser of the solutions that we can offer. We talked about a few customers. We looked at reference architectures. There's certainly more. Our solution architects will be happy to work with you for any specific use cases you may have. Please get in touch with us if you have any requirements or questions. Get Started Today is my invitation to you is to read more if you're interested. We have interesting blog articles. Our documentation itself will help you get started with Greengrass and RoboMaker. We also have published a number of open source assets that can help you accelerate your development and operations. We also have a number of training and certification curriculum that is available for you to access and utilize, and I would strongly encourage you to take a look at what we have available. So thank you once again for joining this session, for listening in. We appreciate your interest. Please don't forget to complete the session survey. It's always useful to get your feedback. Thank you once again.